Welcome, friends. Today we'll discuss quantum consciousness unscripted. Because I read an article that adds fuel to the fire of this theory, which says that what we call consciousness is actually a quantum effect of the brain. As usual in these freely spoken videos, please encourage me by sharing and try to watch until the end. Because I can't imagine it's going to be less than 30 minutes, I don't think I'll make it. Here are the points. At the beginning, let's talk about what people understand by quantum consciousness. In the second part, we'll talk about the latest results. For that, we need to take a step back and move away from the theory of physicalism. Physicalism is that philosophical theory which says that everything can be explained by physics. I wrote in, what is the difference between a child and a laptop? That I am not a physicalist. In other words, I believe just as many philosophers do today that we have something extra. And in this book, I name one of these things, which is qualia. Is it the subjective sensation? Subjective sensation, subjective pain, pain feels painful. It has an extra quality, hence qualia, an added aspect compared to the atoms we're made of. Because nowhere in the laws of physics does it say that atoms feel pain. Yet this collection of atoms, which is my body and my brain, feels this pain. So, in other words, I, as a person, have something extra compared to the atoms I am made of. Well, and in this video, we're stepping outside the framework of physicalism. So we're going to admit that what we call consciousness has something extra compared to the atoms our brain is made of. And to see what that extra thing is, we turn to the notion of a neural correlate. What does that mean? It's clear that not all the atoms in our body participate in consciousness, right? Some atoms do their job without us being aware of it. We don't know what's happening in this cell, or in this cell, or in this cell. The processes that we are aware of are found in the brain. And since not all neurons participate in conscious processes, we call those neurons that do participate in conscious processes a neural correlate of consciousness. No one knows what the neural correlate of consciousness is, and we shouldn't imagine that it's always the same neurons. Is it possible for this neural correlate of consciousness to change its position in space and time? Certain neurons may be involved in conscious processes at times, then others take over. The hypothesis made within quantum consciousness is that this neural correlate has a quantum characteristic. It is a quantum neural correlate. We need to explain what we mean by quantum. And now I'm going to make a small digression as quickly as possible to tell you the essential elements of quantum theory. The first thing is the notion of quantum superposition. This is a classical object. It's the clock with which, well, I say when the recording is good. This classical object can only be in one position. It is either here or here. But in the world of elementary particles, we know that electrons, for example, have the ability to be in a quantum superposition, meaning they are both here and here. So if this clock were to behave quantumly, it could be put into a quantum state where it is simultaneously both here and here, and this state of quantum superposition is what we call quantum. So from now on, when we say the word quantum, we always have to imagine quantum superposition. There is something that is in two ways, in two places, simultaneously at the same time, something that couldn't have happened classically. Yes, in quantum mechanics, in quantum physics. The behavior of this quantum object, which is in a state of quantum superposition, is described using probability waves or probability functions. They tell us what the probability is of finding this object in one place or another if it is in a quantum superposition. Because here comes a second principle of quantum mechanics, which is very important for today's discussion, which is quantum collapse. If this clock is put in a quantum superposition, yes, and I look and want to see where it is. Where that probability will collapse, yes, into a situation where it describes the clock in only one position. So I will never be able to see with my own eyes this clock in one position, both here and here and here, in a state of quantum superposition. Because if someone prepares this state of quantum superposition for me, let's say a very smart physicist, I come and look. The moment I open my eyes, that entire quantum state collapses, it changes, it suddenly disappears. we could say, and the clock ends up in a position that is fixed, either here or here or here. So when I open my eyes, I will find the clock, let's say, just here. This notion of quantum collapse is very important, right? So it's not that the clock was before either here or here or here, and when I look, I find it in one of those positions, because that's where it was before. By no means the clock was actually in all situations in quantum superposition, and when I opened my eyes, that quantum superposition suddenly transformed. Where did that probability suddenly transform? In such a way that it describes an object where I see it. So it's a physical transformation, as real as it gets. The third very important thing for our discussion about quantum consciousness is that not only can an object be in a state of quantum superposition, but also a collection of objects. We call this a multi-particle state, meaning that at the same time the clock and the glass are here, then simultaneously they are here, then simultaneously they are like this, then simultaneously they are like that. I have already described 4 classical states. And when this system of the glass and the clock is in a quantum multi-particle state, it is simultaneously like this, and like this, and like this, and like this. Well, and now I have to talk about quantum consciousness. Yes, I have it here on the printed sheets, and no, there's nothing, so to speak, to be both in this matter. Quantum consciousness means nothing other than that the neural correlate of consciousness I was talking about at the beginning is in a state of quantum superposition. If it were classical, at some point, this neuron would have been here, this one here, in a certain situation. Yes, just one situation. Now that it's quantum, let's keep it this way. I understand, this neuron does this, that one does that. This is a classical state, but we also have another classical state where the first neuron is in a different situation. It's in a different situation and so on, yes. And the system, the brain, the quantum consciousness, is in a quantum superposition state of the 2 classical combinations. Or more, of course. What are these elements from quantum mechanics that fascinate philosophers so much, some of them, that they say our consciousness could be quantum? Because what fascinates them, essentially, is a gateway to those extraneous ingredients, which we need to add to this matter in order to gain subjective sensations and even free will. Well, and I have the elements here. The first, subjectivism. It's clear that what we feel, only we feel. Someone else doesn't really know what we feel. Someone can imagine what it's like to be in our situation through neurons. Mirror. That means he has some neurons in his brain. He looks at us, and those neurons reconstruct the situation we're in. For him, in such a way that he also feels what we felt in that situation. But be careful, this is not a direct feeling, it's a feeling, let's say, mirrored. They recreate that situation mentally. The subjective sensation always remains philosophical for us. What we truly feel, only we know. I have a comparison with quantum mechanics, which comes close to this subjectivism, namely that no one can ever measure precisely what the state of a quantum system is always. They want to see the classical superpositions that make up the quantum state. Because every time he measures, he causes a quantum collapse and gets a result that is often classical. So he influences the measurer. It's fundamental in physics, right? So that means every time you measure, you cause a quantum collapse and you never know what the quantum state was before the measurement. I'm referring here to the general cases, and always, I'm not talking about special cases where you prepare it and then measure it the same way and then you know what it was. Well, that seems very similar to the state of subjectivism to me. I mean, if this consciousness has a quantum nature, yes, only we can know how that thing feels. No one from the outside, no matter how much they measure, because they would cause the quantum collapse. The second thing, the importance of quantum collapse. Because it's been known since quantum mechanics began, and there were physicists who flirted with this idea that what is actually responsible for quantum collapse is, in fact, consciousness. They say this: if we have a quantum system in front of us in a state of quantum superposition and we measure it, it will collapse. But who is responsible for that collapse? Is it the measuring device? Is it the eye that looks at the result of the measuring device? Or ultimately consciousness? And they flirt with the idea that in fact consciousness is the one that ultimately dictates the quantum collapse. This is best seen in Schrödinger's cat, right? Where we imagine that the cat is in a box. And through a mechanism, it ends up in a state of quantum superposition, both alive and dead. Because there is a mechanism there that triggers radioactively at some point, and that mechanism causes the cat's death. But that mechanism itself is in a state of quantum superposition, and so the system evolves. Yes, inside the box, in a state where the mechanism has triggered, and the cat is dead, and in a state where the mechanism has not triggered. And then the cat is alive. So, inside the box, the cat is at the same time in a living and dead state. And furthermore, yes, if a robot in this theory, once again of quantum consciousness, yes, if a robot opens that box, the system will still be in quantum superposition. So we will have a robot that finds a dead cat in a quantum superposition with a robot that finds a living cat. And this system will finally collapse only when the I and consciousness, actually not so much the I but the consciousness of a person, looks at that situation. And then the system collapses. That is, we will have either a dead cat with a robot that sees a dead cat and a person who sees a dead cat, and a robot observing the dead cat, or the other case. Famous physicists like Schrödinger and Wigner have considered this idea and said so. The systems in front could have reached a state of quantum superposition and would have continued in a state of quantum superposition, as long as no one with a consciousness would have looked at it. In other words, the universe itself could have been in a state of quantum superposition until a conscious being looked at this universe, the planets themselves could have ended up in a state of quantum superposition. In this theory, yes, until a being looked at them. And at that moment, his consciousness was the one that triggered the quantum collapse, and the planets reached a classical state, only in one of the possible positions. Does that seem strange to you? But I know it's strange, but it's an extraordinary hypothesis. And even if it's not one of my favorites, I also talk about it at the end. I want to say this. It's clear that if we move away from physicalism and want to explain consciousness, we need extraordinary hypotheses. And yes, the fact that consciousness is what triggers quantum collapse is such an extraordinary hypothesis. We come to the third point, the importance of quantum collapse. Because, pay attention, it's not only when we look at an external object that is in a state of quantum superposition just because we are looking. It involves a quantum process, and in this theory, our brain is considered a quantum correlate. And it is in fact the one. That's actually where the quantum collapse happens, because it is correlated with what we see in front of us. So in other words, when we look at that planet, let's say that planet collapses in front of us, being a quantum superposition. What actually happens is that that quantum system has correlated with the neural correlate of consciousness, which was also in a quantum state. And in fact, it is this neural correlate of consciousness which has a state of quantum collapse, and automatically that planet also has a state of quantum collapse. Well, and this philosopher Harry Stubbs says this, gentlemen, in fact, this process of quantum collapse of the neural correlate of consciousness, yes, is the one that creates subjective sensations. He calls this in his books the Heisenberg event, meaning that neural correlate has a collapse at some point, and then I have it. A subjective sensation that is associated with that particular collapse state, yes. So the subjective sensation, for example, of the color green that I see at a certain moment. Yes, because my brain was in a quantum superposition and could have seen other colors too, like a darker green or a lighter green. It depends on how much that quantum state has evolved and when it undergoes a quantum collapse. This Heisenberg event is the subjective sensation. That's when I really see the color green and that extra thing I mentioned earlier. So here is that ineffable extra thing, right? Which is added matter and which makes it possible for us to feel subjective sensations. So it's something extra because it's a subjective sensation. But why do Aristotle and the other physicists favor this? Because it's within a known physical theory, namely quantum mechanics. Well, and the last thing, because after that I'll get back to the article I want to talk about, is that this leaves a loophole for free will. I mean, what happens with a quantum collapse? Normally, quantum collapse has a random outcome in quantum mechanics. What does classical quantum mechanics say? That if we look at a system in superposition, it will collapse into one of the classical states that make up that superposition system. That's if we make a classical measurement. And pay attention, the result has a probability distribution, but it is intrinsically random. Anyway, this could also happen in the brain, but as some say. By the way, we could introduce free will here. I mean, if that state of quantum collapse of the neural correlator of consciousness, if that state could somehow be influenced by something else, by free will, then it would result in either this or that. Simply put, it would result in either me raising my right hand or me raising my left hand. And this, of course, has a major problem, because if someone from the outside were to look at the neural correlate of consciousness, they would expect a statistical distribution, meaning to collapse into this state, to collapse into that state, to collapse into that state. Whereas, if that person always wanted to raise their left hand, do they want to break this system, so to speak? The one who measures the neural correlate of consciousness will always see a certain result. So, we will have a statistical distribution different from the one predicted by quantum physics. Well, but this is an extraordinary hypothesis, and we remain within this extraordinary hypothesis, recalling the contribution of Roger Penrose, who received the award in turn. You know, a mathematician and physicist, and Stuart Hameroff, an anesthesiologist. He asked, "Sir, when does consciousness leave the brain when I anesthetize someone?" And he made a connection with some macromolecules called tubulin. Now, it's important to say that these molecules are part of the structure. I think it's called the skeleton, something like that, of the cell. These are found in most cells, but here we're focused on neurons. And they say this, Penrose and Hameroff say this, that this tubulin is found in a state of quantum superposition between two possible states. I think this is called a dimer in chemistry, and that in the brain it reaches states of quantum superposition. And so it's very important, we're not talking about a single tubulin, we're talking about many more tubulins, which are scattered throughout the brain in such a way as to form a neuronal correlate of consciousness. And that each of the tubulin molecules is either like this or like that between the two situations. And so basically we will have quantum superposition states spread across multiple tubulin molecules in a very large area of the brain. And that in this way, yes, we will have that quantum structure, that quantum superposition, which would form that neural correlate of consciousness. It's quantum here because we need quantum superposition for today's theory. Ever since it appeared, this theory of Roger Penrose has faced strong criticism from physicists. One of them is Max Tegmark, who showed that the superposition state of tubulin could not last. Inside a warm and wet brain, as they say, yes, just like our brain. We know that these quantum superposition states are very fragile. The larger the objects get, the more fragile the quantum state becomes. It resists less and less to interaction with the environment. Yes, that's called decoherence. Because of this, for example, quantum computers that create qubits have to cool the whole system to a very, very low temperature so that this interaction with the environment is reduced. He shows in the physics book, he tells these arguments that are against Roger Penrose, these physics arguments, and which essentially are very strong. This macromolecule is quite large, and it's hard to imagine, knowing the known physics, that it could indeed withstand interactions and not reach a classical state due to the collapse caused by the surrounding environment. But now, while working on this video, I realized how much I could have been wrong. Because these physics-based arguments against the idea that this tubulin could be in a quantum superposition state are based on the physicists' hypothesis. Both mine and many others, their belief, so to speak, that this quantum collapse state can be caused by the surrounding environment. But be careful, this has a fundamental problem. Actually, right now we're within the framework of quantum consciousness theory, do you remember? The collapse is caused solely and exclusively by consciousness. In other words, in this theory, that tubulin can very well reach a state of quantum superposition, because the only thing that can cause the collapse in the end is quantum consciousness. I don't know if you see this argument, but it seems so strong to me. I only just understood it. Yes, because Max Tegmark's argument against the idea that tubulin remains in quantum superposition is only valid if you assume that the collapse is caused by the surrounding environment. But if indeed those who believe in quantum consciousness are right and only consciousness, only it, can collapse the system, then it makes sense. Yes, interactions with the environment, yes, will only serve to limit the states that are in quantum superposition. But in the end, tubulin, in this theory, could reach a state of quantum superposition, and the choice, in the end, the quantum collapse, could be caused by quantum consciousness. And now we've reached the article that gives a boost, that adds fuel to the fire of this theory of quantum consciousness. And what does this article say? First, I'll summarize it briefly and then I'll explain it a bit more broadly. Briefly, it says this: Mr. Tubulina, this is a protein, it contains amino acids and it's not very big. It's about 4 nanometers this way, about 8 nanometers that way. Inside it, there is a special amino acid, tryptophan E, special because it has phosphorescent characteristics. This case is even more special. Let's see why. Well, A. In the structures formed by tubulins gathered together, yes, thousands, tens of thousands of amino acids have been found. Tryptophan, which together form a multipartite quantum superposition state. Note, we're dealing with thousands or even tens of thousands of these molecules. Tryptophan, which together form a quantum superposition state and a state that extends over a fairly large dimension. We're talking about approximately 100 nanometers. Alright, so let's explain what we meant starting from this picture, okay? In the upper left, we see tubulin, which is made up of 2 parts. Yes, I think it's called a dimer in English, with 1 alpha and 1 beta part. One is colored red, the other is blue, and together, the 2 parts form the tubulin molecule, which isn't very big. I said it's around 4 nanometers one way and 8 nanometers the other. It's just that in neuron and cell structure, tubulin molecules are organized into what are called microtubules. And that's what you see in this picture. I mean, if we look at B, we see here red, blue, red, blue, red, blue. So those tubulin molecules form an almost spiral structure. If we look at figure C, we see that this spiral structure, which is like a very long tube, itself forms a structure of circular tubes. Yes, and that's what we see in C, and in D we see that there are several of these circular tubes placed next to each other. Yes. So now we're talking about microtubules, or rather bundles of microtubules. And such structures, these bundles of microtubules, can become very large, on the order of micrometers. This picture is important. On the left side we see tubulin. In the black middle area we see the microtubule structures that form very large bundles. And on the right side, the positions occupied by tryptophan in these microtubule structures are drawn. Because that's what we're talking about. That special amino acid that will reach a state of quantum superposition. And we see on the right side how these tryptophan structures are in the end ordered. And now what the article tells us is that not only are these structures ordered by tryptophan, but they also form together a multi-part quantum state. That is, they are in one way or another in a state of quantum superposition all at once. We are talking about thousands or tens of thousands of tryptophan molecules forming a quantum superposition together, which extends over dimensions of about 100 nanometers or so. How should we picture this structure? Let's imagine a classical state. We assign this energy level to the first tryptophan molecule, this level to the second, and this level to the third. And this forms the first substate. After that, the same system can also be in another substate. That is, the The first molecule is actually at a different energy level. Another molecule is at another energy level, let's say, oriented a bit differently, and so on. This entire system of tens of thousands of tryptophan molecules exists in a quantum superposition of these combinations, which we can simply refer to as plastic. So that could be it, essentially, right? The place from where we could start toward the state of neuronal correlate of consciousness. Because, look, in the brain we would have multi-particle states that extend over very large distances. Here we basically need to talk about two things: how it was measured and what these states represent. The measurement relies on fluorescence and a much more complex extension of fluorescence in the quantum domain, which is called superradiance. No, what is fluorescence? We know fluorescence, right? In objects that are fluorescent. We have atoms or molecules that at some point receive electromagnetic radiation, light, right? Those atoms get excited by receiving the photon from the light, and then they de-excite, emitting light in turn. But the packet of light energy that leaves has less energy than the initial energy. Superradiance is a superfluorescence effect which is caused by multiple molecules. Careful, it's a purely quantum phenomenon, yes. And we can explain it as follows. We have several molecules and they all act like dipoles. We have an electromagnetic wave. Technically, it's the probability wave of a photon, but we'll call it an electromagnetic wave or light for simplicity. And it has a wavelength, yes. In the case of these measurements, it's somewhere around 200-something nanometers. That means that in an area smaller than 200 nanometers, the electric field is roughly the same for all the molecules. And that makes all those dipoles oscillate synchronously in that electric field. If we think classically, once again, by all oscillating synchronously, they are then able to absorb the incoming light and generate another light. All at once, so not each one in turn. Well, and we should explain this phenomenon from a quantum point of view, not from a classical point of view. We're considering fluorescence, and let's assume the molecules are independent, right? Then what would happen? A photon from the light is absorbed by a molecule, then the molecule gets excited, relaxes, and emits another photon. Another molecule also absorbs the photon, gets excited, relaxes, and emits another photon. All these photons are in coherence with each other, yes, and they are all emitted at a certain moment. Delta t, which I understand is on the order of nanoseconds after the initial photon has been absorbed. But if this system of molecules is quantum, meaning it is in a state of quantum superposition, so those dipoles are aligned, they are ordered, and they are able to form those quantum superposition states we're talking about. What happens? When the electromagnetic wave comes, this whole system gets excited to a higher state and then suddenly de-excites. This means in practice that we have two effects. This system, when it releases, will emit light because once again it absorbs photons from the incident light and then emits photons. The photons emitted by this system are released much faster than before. What will we measure? A much faster, shorter, and more intense response. So basically the energy will be the same, but it's just that the light coming out has a much higher intensity for a much shorter period of time. And if we observe this in the experiment, that's a sign that all those molecules were a quantum system. They were in a state of quantum superposition together. They didn't act independently. As with fluorescence, we have superluminescence, not superradiance, since superluminescence is different. Well, so this article demonstrated that these tryptophan molecules from the macromolecule, that big thing, are in a state of quantum superposition. Yes, and there are a lot of them. We're talking about tens of thousands which together form a state of quantum superposition. They not only did numerical simulations, but they also made measurements. Thank you for your attention. What time am I saying this right, sir? Is this an argument for quantum consciousness, or is it not an argument for quantum consciousness? I would like to draw your attention to a few things. First of all, It is indeed a state of quantum superposition of tens of thousands of tryptophan molecules, which, pay attention, together form this state measured over only about 100 to 200 nanometers. So that state doesn't extend over millimeters or centimeters, as it should happen in the whole brain, to eventually form quantum superposition. This state is very small in size. Now, it could be even larger. It's a very relevant question, and it's possible that it could be. They measured it over this small distance because they used fluorescence and this ultraviolet light, which has a wavelength of 200 nanometers and something. So, if it was somehow on a larger scale, they couldn't have measured it. That's the first thing. And the second thing, right? It's surprising, Torp. So does this happen or not? Because we see that it's a state at room temperature with a lot of molecules, tens of thousands of molecules. From my point of view, it's not surprising at first glance. I sit and wonder why I didn't think about this before. I don't know. But why isn't it surprising? Because if we look at the structure, this tryptophan inside actually forms a regular structure, just like it happens in solid materials. Where in solid materials? We know that at room temperature, we can have these quantum superposition states. On larger scales, yes. We're not talking huge, because then we should have them in super content, but on larger scales, we can have them. Because the atoms are very orderly. It's a system, yes, just like solid state matter, yes, of essentially ordered molecules. So then, it's not that surprising that we have this quantum superposition state, right? Tens of thousands of tryptophan molecules over a distance of a few hundred nanometers, because these tryptophan molecules are well arranged. Ideally, we should see if this multipartite quantum state of tryptophan extends over much larger distances. Not just 100 nanometers, but across distances large enough to cover nearly the whole brain. Yes, because then it's about quantum consciousness. The quantum state is just extremely fragile. So we're not just talking about tryptophan molecules? 10,000 that are inside such a bundle of microtubule, which is quite orderly. But I imagine that we have several bundles of microtubules and they start to become disordered. So, I imagine that it's very hard for the quantum state to extend from a single bundle of microtubule to another bundle of microtubule to yet another bundle of microtubule, at distances of millimeters or centimeters away, because all these systems interact with the environment they're in. The quantum state is short-lived due to coherence effects. That's expected. However, I see I have 4 minutes left. Yes, do you know what the problem with this argument is? I told you earlier, right? Well, if we're talking about the theory of quantum consciousness, the collapse is produced only by consciousness. And then, within this consciousness, the collapse couldn't be produced by these things that are thermal. Interaction with the thermal environment, gravity, or any other theory, none of these things can cause the collapse. So, within this theory, yes indeed, these tryptophan structures could extend their coherence throughout the entire brain. Because, once again, the collapse is not caused by the environment, by the surroundings, but it is caused by consciousness itself. Well, personally, I don't believe that. That's just what I think, yes. I don't believe that consciousness is really the one causing the quantum collapse. Personally, I believe in an objective physical mechanism, right? What could be inside quantum gravity? We might discover that as a molecule gets bigger and bigger, yes, it actually causes quantum collapse. And there are such theories, or well, other theories that are called objective. They're not subjective, yes. But anyway, this theory itself is fascinating, and I can only end with that. It's good to know these things, right? And that's the end. If you haven't subscribed to this channel, you can do so by clicking this subscribe button. I want to thank everyone who contributes on Patreon. Until next time, I'm Christian Presura. You are cool. All the best. Goodbye.